Hey everyone. Today we're going to be learning about projectiles. What's a projectile? Well, before we get to that, we have to define a term known as free fall. Free fall is any motion where gravity is the only force acting on an object. What are some examples of objects moving in free fall? Well, here's a person who's dropping a really heavy anvil and is falling down a really great distance and smacking into something down below. When he's holding the anvil, it's not in free fall because there are multiple forces acting on it. For example, his hands are applying a force that's keeping it upright and preventing it from falling. But as soon as he lets go, gravity is the only thing that's acting on that anvil. So you'd say that the anvil is in free fall after he lets go of it. Here's another example. This is a clip from a TV show where someone is flipping a coin. That coin moves up and then slows down due to gravity's pull and eventually comes back down. And as long as we only look at the coin when it's in the air, we could say that the coin is in free fall. But again, if he's touching the coin, then it's not in free fall because then the hand would also be affecting the coin. Here's another example of free fall. This is an Olympic ski jumper going off a ramp, and they are not in free fall until the moment they leave the ramp. And at that point, gravity is the only thing affecting the jumper, and so that's when they are in free fall. And then one last example. Here's someone kicking a soccer ball, and as it is floating through the air, making that nice arc path that we're going to become very familiar with in this unit, it is in free fall, as long as we're not talking about the moment where he kicks it or the moment where it lands. Everything in between is free fall. And free fall is going to be a really important term because it's where all of our physics problems in this unit are going to be happening. So now we can finally get to defining what a projectile is. In short language, a projectile is any free-falling object that is moving in two dimensions. So think about all the different dimensions in our universe. There's length, width, height, and even time, if you want to go into the fourth dimension. And so what does two dimensions of motion mean? Well, in a math class, you're used to working with two dimensions. There's the x dimension, which is horizontal or left and right, and there's the y dimension, which is the up and down. So those are the two dimensions that we're going to be operating in now that we're studying slightly more complex motion than what we're used to. So the vertical dimension, that is up and down, is always going to be accelerated for projectiles. What does that mean? It means that things will get faster and faster and faster in that direction, but they won't necessarily get faster and faster to the side. What's the difference? Well, when we're near a planet, gravity is going to make things faster and faster in the downward direction. So let's look at an example of a projectile so we can start to get used to how they work. Let's imagine that there's a monkey standing on a cliff, because that happens, totally. And monkeys tend to throw stuff. We know that from the last time we visited a zoo. So this monkey has an orange, and he decides he wants to get rid of the orange. So he could toss it, he could drop it, he could do all kinds of things. Let's imagine a situation where he drops the orange, and then let's analyze what happens in the 3 seconds afterward. 1 second later, the orange is going to be some distance below where it was dropped, and it will have picked up some velocity. So we could say that the velocity in the y dimension is larger than 0. It could be 1 meter per second downward, it could be 2 meters per second downward, we don't know what it is, but it's definitely downward, and it's definitely not 0. If we wait another second, the position of the ball, or the orange, is going to be even lower than before, and it's going to be traveling with a greater velocity in the y dimension. Notice I've got that letter y kind of small next to the v. The v, of course, stands for velocity. The y stands for the y direction. So that's what the subscript tells you, is the direction of motion that I'm describing. And finally, in the 3rd second, the orange would be even farther down. It would now be traveling a great distance every second. So the space in between each second is getting bigger and bigger. And similarly, the velocity is getting faster and faster. So this is what we would call the dropped path for the orange. This is the motion of the orange as it is let go of and released without giving it any oomph or any push. So now we're going to switch mindsets and think about a different scenario, something different that the monkey could do. He could change his mind and say, I don't want to drop it, I want to throw it. So he could toss it to the side with some horizontal velocity. We would call that horizontal velocity Vx, which means velocity in the x dimension. Now I'm going to suggest something kind of strange here, but bear with me. Let's imagine that this scenario is happening in outer space, which is kind of a weird thing to bring up. Why would I suggest this? Well, in outer space, there's very little gravity, right? Not no gravity, but very, very little. And so if you imagine a situation where there's no gravity and the orange has just been thrown through space, what is that orange going to do? Well, if you've seen movies with things happening in space, depending on the movie, you may have seen what would happen. It would just keep on going at the same velocity forever. until something causes it to change its motion later on, like slamming into something. So in outer space, just like in the x direction, which, by the way, we call this the no gravity path, in that path, there would be no change of speed. On Earth, gravity only affects what happens up and down. It doesn't affect what happens left to right. So this is what we were saying before, that there's acceleration in the y direction, but there is no acceleration in the x direction. So let's take these two different scenarios and let's see if we can combine them to figure out how projectiles really operate. Let's connect these lines right here that represent the vertical position and the horizontal position of the orange after 1 second. And let's do the same thing at second number 2. And let's assume that the orange is going to be at those locations. And let's do the same thing with second 3. So again, I've connected these lines here, and these connecting points would actually be where the orange really is after 1 second, after 2 seconds, after 3 seconds. So do you recognize anything here? This is the parabolic path, which is a fancy way of saying a curve. This is the path that projectiles take when you throw them horizontally. Anytime you've ever thrown a baseball or a football or any kind of ball ever, it doesn't go in a straight line towards where you threw it. It arcs. It goes up and then down. And if you throw it straight, it doesn't go straight. It arcs downward. So this is what causes the arc when an object is thrown or thrust into the air. It's because it's traveling along at a pretty constant velocity in one direction, and then in the other direction, it's actually speeding up. It's not traveling at a constant velocity. So when you combine those two types of motion, you get this arc pattern. And that's a pretty good introduction to a projectile. Now, there's a lot of things you'll need to know about projectiles in order to solve problems with them. So there are 5 assumptions that we're going to make about projectile motion. And then when we're solving problems, we can rely back on these assumptions to help make solving those problems a little bit simpler. So here's projectile assumption number 1. First, take a look at what's going on here. There's a guy here who has a device that allows one sphere, which is identical to the second sphere, to drop, kind of like the monkey dropping the orange. And then on the other side, that same sphere with the same mass and properties and everything is being launched to the side, completely horizontally. And what you notice is that the objects fall at the same rate. Even though one of the objects, the one on the right, was given some extra velocity to the side, they still end up hitting the ground at the exact same moment. So what does this tell us about projectiles? It tells us that the vertical and the horizontal dimensions do not affect one another. In other words, it doesn't matter what you're doing left to right. Gravity only cares what you're doing up and down. And those two dimensions do not affect one another. We can think about them completely separately because clearly they do not affect one another. So that's projectile assumption number 1. Let's look at projectile assumption number 2. This assumption is one that maybe you already know. It's that for any object that is in free fall, meaning again only being influenced by gravity, the vertical acceleration of that object is going to be equal to negative 9.81 meters per second squared. Again, you've probably seen that number before. It's the number that describes the rate of acceleration of any object on Earth's surface that is allowed to fall. So whether you're on top of a cliff dropping something, in which case the acceleration due to gravity would be negative 9.81, or whether you're throwing something into the air, still negative 9.81, or whether you throw something in sort of a two-dimensional motion, maybe you throw it to the side as well, still the same number will be true. The acceleration due to gravity in the vertical direction is always going to be equal to negative 9.81, unless you get on a spaceship and go to another planet, in which case this number will change. But on Earth, you can rely on this number. Notice that the vertical velocity of these objects is going to change. The velocity will be constantly changing from 0 to some other number, and then maybe back to 0. It depends on what's going on. But the acceleration is staying the same. So here's not a new assumption, but this is actually showing what the last assumption was just saying, that there will always be a constant acceleration downward of negative 9.81. Now this animation that I found on the internet is showing the number 10, and we use 9.81, but they're just rounding, so that's the same value they're giving there. So on the left, you can see that as you throw something into the air, its velocity is constantly going to be changing, but the acceleration will always be that consistent 9.81. And when you plug it into formulas, you should plug it in as negative 9.81 because it's directed downward, not upward. Okay, back to our assumptions. This is projectile assumption number 3. For any object in free fall, only being influenced by gravity, there is no horizontal acceleration. In other words, acceleration in the x direction, or ax, is equal to 0. You can see in the animation that there's an object being launched at an angle, and the green lines are tracking its motion in the up and down direction, and there's a line tracking its motion in the horizontal direction, left to right. And you can notice that the velocity on the side there, it does change. It looks like it starts out faster at the bottom and then slower at the top. So there's definitely some acceleration in the y direction. But then if you look at the bottom, on the x direction, that arrow is just moving across, moving across, moving across, and it's not really changing its speed. So that's showing visually what that assumption up above is saying, that there is no horizontal acceleration. It stays the same constant velocity all the time. And that's what it says on the bottom. It says, notice that the horizontal velocity never changes. Whereas in the previous example, when we were looking at things going up and down, that up and down velocity did change. So horizontal things, therefore, are going to be a little bit simpler. We'll talk about that in a minute. Here's projectile assumption number 4. This is perhaps the most useful one in terms of helping you solve problems mathematically. And it's that the amount of time that it takes to move vertically, ty, is the same amount of time that it takes to move horizontally, tx. In other words, time in the y direction equals time in the x direction. To explain this assumption, I have a visual here of someone being kicked in the face with a soccer ball. And as that guy kicks the ball moves side to side, but it also moves in the upward and downward dimension. So there's kind of both dimensions of motion happening there. So one question I could ask is, how much time does the ball take to move vertically up to the height of the face of the other player? And a second question I could ask is, how much time does the ball take to move horizontally to the other player, like to get to the distance away that he is? Those are two different questions with technically two different answers, but the value of those answers would be the same. So if I had a timer, I could look and count and say, okay, start my timer now, stop my timer there where it hits his face, and that'd be about 1 second of time. And I could get that same amount of time whether I'm looking at the horizontal or I'm looking at the vertical. So those two times are equal. So on the very bottom here it says time is the one thing that's in common between the vertical and the horizontal. And that means you can use it as a bridge to solve different types of information going from one thing to another. So time is going to be very important for you to be able to solve for in a projectile problem. Here's the final assumption, projectile assumption number 5. To solve for vertical information, that is things like velocity in the y direction and acceleration in the y direction and displacement in the y direction, to solve for vertical information, we must use kinematics. That is one of the 4 kinematic equations, because the object is accelerating vertically due to gravity. In other words, we need a kind of complicated equation to solve for up and down stuff, because the speed is changing, so it's a little bit of a complicated type of motion. But on the bottom it says, to solve for horizontal information, we can use simpler physics equations, such as displacement equals velocity times time, since there is no acceleration happening. In other words, when the speed is really constant, that's pretty simple physics, so we don't need to use really complicated equations. We can just use distance equals velocity times time. So these two dimensions, the up and down and the left and right, are going to be treated a little bit differently because they have different amounts of complexity. So there's your 5 projectile assumptions. I want you to be able to see them in action. So here is your first ever sample problem with a projectile. Here we go. A projectile is fired horizontally at a velocity of 20 meters per second off of a 122.5 meter tall cliff. What will be the range of the projectile? Now, the range of the projectile, that's a word that we should probably learn. That word means how far it goes horizontally. So if you were to drop a measuring tape down to the ground right here and then ask how far from that point will it go, that's the range, versus the height, which is this 122.5. Okay, so where do we even begin solving a problem with two-dimensional motion? It seems much more advanced than what we've done before. Well, it's actually not going to be much more advanced because we just have to remember how projectiles kind of work like kinematic problems that we've already learned about. So I'm going to take this image and I'm going to add a little bit to it. I want to show that there are 2 possible paths that this cannonball could go in after it's fired out of the cannon. It could go straight down if the cannonball was just dropped, and we can see what that path would have looked like. And if we were in outer space and the cannonball was fired forward, we can see what that path would have looked like. And then if we combine those 2 paths, what we get is the actual motion of the projectile. Now remember, projectile motion assumption number 1 was that these 2 dimensions do not affect one another. So we don't actually have to think about the real motion of the projectile. We can instead just think about the independent two different paths, and we'll end up getting realistic answers because the two paths don't affect each other, so we don't have to combine them in our minds in any way. Here's what I mean by that. I'm going to start out trying to solve for the amount of time that it takes to vertically fall to the ground. That cannonball is going to be in the air for some amount of time. It could be 5 seconds, it could be 1 second. Whatever that amount of time is that it's falling down, that's going to determine how much time it spends going forward as well. So at the end of my question, I should be able to know how much time this thing spends falling, because that'll be the time that it spends going outward, and then I'll figure out how far outward it goes. So let's just figure out how much time it's going to be in the air for. For that, I'm going to use only vertical information. That was one of our assumptions, that to find vertical information, you have to plug in vertical information. So the first one I'm going to look for is x, y. Here's where the letters start to get confusing. This x stands for displacement, which means how far the cannonball is going to travel, and the little y stands for the y direction, meaning up and down. So what is the displacement in the y direction? That's my first variable. The second one I'm going to look for is the initial velocity in the y direction, then the final velocity in the y direction, then the amount of time it spends falling, and then the acceleration in the y direction. Notice I'm basically just setting up what I usually do for one-dimensional kinematics problems, which is list out my 5 variables, and then I'm going to try to plug in what I know. But there's a little subscript y on all of these now, because I'm only going to use information that relates to the up and down motion of the object. So what do I know about the displacement of a cannonball? Well, as long as I'm only talking vertically, I know how far it's going to fall. It's going to fall downward a distance of 122.5 meters, so my displacement is negative that number. What about the initial velocity? Well, is that 20 meters per second? Because up there you can see there's a velocity at the beginning of 20. Well, it's not 20 because that 20 is horizontal information, and currently I'm looking only for up and down information in the vertical. So I'm just going to look at that dropped path. You should know by now that if you drop an object, the initial velocity is going to be 0, and I'm sort of pretending that that is a dropped object right now because I'm only looking at its vertical motion, which looks like a drop. What about the final velocity? Well, we don't know the impact velocity when it hits the ground, so I don't know that information. We also don't know time. That's what I'm going to try to solve for. And we do know that the acceleration due to gravity is negative 9.81. Now in this case, to match up with a diagram I'm going to show you later, I'm shortening that a little bit to just negative 9.8. Doesn't matter which one you use, they're pretty close. So with those numbers, I can now do what I'm already trained to do, which is pick a kinematic equation that will help me solve for the unknown variable that I want, which is time. The equation I'm going to choose is this one. And this equation is the one I'm going to choose because it has time in it, which I can solve for. And it has other variables that are known to me, such as x, vi, and a. So the only problem with this formula is that to solve for time, time is in 2 locations, so maybe you know the trick for how to simplify this formula. Vi is equal to 0 in this case, so I can plug in my mind 0 for vi, and I know that 0 times any amount of time is just going to be 0. So that whole term is 0, therefore it doesn't need to be in our formula because it contributes nothing in this particular situation. So now my equation is shortened to x equals 1/2 at squared. That's a much easier equation to work with, and we can more easily rearrange that to solve for time. So I'm going to multiply both sides by 2 and divide by a, and then the last step of rearranging this with algebra to solve for time instead of time squared would be to take a square root of both sides. So now that I've rearranged my equation, these are the things I'm going to plug in, x and a, in that order there that you see. And this is what it would look like. Square root of 2 times the displacement divided by the acceleration. Notice that there ends up being 2 negative signs inside of that square root, and that's good because you can't take the square root of a negative number, and your calculator would give you an error if you tried to. So if you ever get that happening to you where there's an error when you're trying to do a square root, it probably means you forgot that one of those values is negative. So the answer that I get in this case is 5 seconds. It is exactly 5, and that's why I changed the 9.81 to just 9.8 because I wanted these numbers to come out nice. So is this our final answer? Well, the question asked, what will be the range of the projectile, which means how far out it goes. So no, this is not our final answer, but it's very important information for getting the final answer. I mentioned before that time, finding how much time it takes for something to move, is going to be the most important thing for you to solve for. So what do we do with this information? Well, now that we figured out how long it's going to take for that ball to fall, we also know how much time it's going to take for it to move outward. because the amount of time to fall is the same as the amount of time to move outward. So I now actually have some horizontal information. So here's my next strategy. I'm going to understand that as each second passed, that ball was going faster and faster and faster because of the gravitational acceleration, but it was only going faster in the up and down direction. If I pay attention instead to the horizontal direction, I can see that that 20 meters per second actually never changed. It's always going to be going 20 meters per second in that horizontal direction. So I know how much time it was traveling for, 5 seconds. I know how much velocity it had in the horizontal direction, 20 meters per second. So I should be able to put those two bits of information together to figure out how far it went horizontally. Here's my strategy for this. I'm now going to solve for the horizontal displacement, also known as the range of this projectile. That's going to be xx. Again, the letters might be a little bit confusing at first. The big X stands for displacement, how far the cannonball is going to travel. And the little x next to it is different. That represents the x direction, which is the left to right horizontal direction. So x in the x direction must be equal to the velocity in the x direction. All right? I can't plug in a vertical velocity to figure out how far it's going to go out. Those don't match up. Those aren't from the same type of variables. So x in the x direction is equal to velocity in the x direction multiplied by time. I have those two variables. The constant velocity in the x direction is 20 meters per second, and I figured out that it's going to take 5 seconds to fall, which means it's also going to take 5 seconds to move across. So 20 times 5 means my final answer for the range of the projectile is 100 meters. Now that took me a little while to solve that problem because I was explaining it, but when you're doing this on your own, you'll be able to progress through problems like this much faster. And by the way, in case you're curious, this was an example of a type 1 projectile. There is such a thing as a type 2 and a type 3 projectile, and those are much more complicated, but this is a good introduction. What identifies a type 1 projectile is if something is launched with only horizontal speed and it's allowed to fall. So that's a type 1, and we'll talk about types 2s and maybe even type 3s another day. So that's it for today. I wish you luck in your studies, and I'll see you in the next video.